AP is very concerned with connecting torque and angular momentum, because we had that torque unit before break, where you learn about how torque is a rotational force, and it's going to make things have an angular acceleration. Now, if things have an angular acceleration, and angular momentum is angular velocity, it must mean their angular momentum is changing, right? So so the equation that we're going to use actually is we're going to say that torque, which is, we use the Greek letter tau as our symbol, is equal to the rate of change of angular momentum. So delta L delta T. So it's just a change in L divided by the change in T. Now, this is also not a new formula. You guys have had something very similar to this in the past. You had a formula for momentum. So that was momentum. Force is equal to delta P over delta T. And so this is actually what we said was the real Newton's law. I mean, there's a little bit more complexities too, because the calculus version of this is more full, more complete. But this is exactly this in a rotational manner. So I'll just write the words out here. So torque, the net torque even, right, is going to be equal to, and the net force is equal to the rate of change of angular momentum. All right. So what you're going to get a lot is you're going to get a lot of problems where they give you a graph. And they say, I've got angular momentum or angular speed on that axis, and I have time on this axis. And then you'll get something like, a line. Usually it's got some data points, and this is a fit line. So it'll look kind of like that. They give you a best fit line. And they say, ask the question, what is the torque? Ooh, the slide, we can see my x-axis. What is the torque on the system? Well, the torque, like we said, let's write this formula again, is equal to delta L over delta T. So in this case, the L, the angular momentum, is my y-axis, and the time is my x-axis. So this is delta y over delta x, which is slope, right? So to find the torque, I just need to find the slope of this line. Sound good? So that's just going to be, rise over run. I think you guys can do that. So it might make you do another problem that's very similar. Let's section that off. They might say something like, given a graph of torque, what is the angular momentum? So if you get a graph that looks like torque and time, let's put some numbers on this one. So we're going to say this is going to be 2 seconds. Let's put seconds as a variable in here. This will be 4 seconds, kind of making that fit, and this will be 6 seconds. Right? I don't need to put the S there because I already have it here. And then on this axis, we're going to say this is going to be, let's say 4. And so I need to put the units here of newtons meters. And then, so the question we're looking for is, what is the change in angular momentum? So what is delta L? So to do this, what we're going to do is we're going to take that same torque equation we've had here, right? But we're looking for L. So if I multiply this guy across, I'm going to get delta L is equal to torque delta T, right? And so what this is this is our height times our width, right? So this is x by y, x times y, and I do x times y, so or y times x, I guess, times x. That is the same thing as finding the area. So I want to find the area of this trapezoid. So because I always have a hard, you can do this with a trapezoid formula, but I always have a hard time remembering that. We could look it up, but you're taking the AP exam, you're doing a test, and you don't have time to stop and look it up or try and think, what's that trapezoid formula, and do I really want to risk doing it wrong if I guess it? So we're just going to do it the long way a little bit, because we're a little more sure. So I'm going to break it into 3 shapes. You got triangle 1, square, you got triangle 2. Right, and these are going to have the same area because they're the same height and the same base. So I just need to find the area of this guy, multiply it by 2. So let's call it, I guess let's go area 1, area 2, area 3. Right? And then total is going to equal the sum of those guys. A2 plus, slide that a bit so you can see, A3. So A1, we're going to say is 1/2 base, which is 2. Let's write BH first. So it's going to be 1/2 times 2 times 4 is the height, right? So that's going to be, have a value of 4. Area 2. Area 2 is going to be 2, have a width of 2 and a height of 4, and it's a square, so I'm just going to do, well, not square, rectangle. 2 by 4 equals 8, but then I now have to double this one. So when I get my total area, which is equal to the change in angular momentum, that is going to be 2 times 4 plus 8. So that is going to have a value of 16. Well, I guess. Yeah, we never talked about the unit for angular momentum, so let's do that over here real quick. So what is the unit for angular momentum? It's going to be, we can do it from this equation here, right? Is what we can think about. Or this one here might be better. What's the unit for torque? Newtons times meters, right? So if I do torque times time, I'm going to get newtons times meters times seconds, right? Or another way we could look at this, we could say L equals I omega, which is going to be a slightly longer way. What's the unit of I? Well, I don't remember either, but I know that moment of inertia has the form of mass times radius squared. So this is going to be kilograms meters squared. And what's the unit for omega? Radians per second. But radians are a fake unit, so we're just going to write 1 over seconds. So that doesn't look the same at all, does it? Dang. Well, let's simplify this. What if I can turn this into newtons somehow? So if I say I've now got, well, Newton, first of all, let's write Newton. Let's kilogram meter per second squared. So I'm going to have a meter left over, right? And I have an extra s on bottom. So if I write like that, hey, that's a Newton. So that's going to be newtons, meters, seconds. So, oops, sorry. If I come over here to where we were before, I can say Newton meter seconds as my unit. All right. Hope this video has been helpful to you guys, and I'll see you in the next one. Stay safe out there.